Imagine you're a farmer who is in charge of breeding rabbits. You went ahead and got yourself a pair of baby rabbits, one male, one female. And the rabbits breed according to the following 3 rules. 1. A rabbit takes 1 month to mature. 2. A pair of mature rabbits will produce a pair of baby rabbits every month, one male, one female. And to prevent people from making math useful, let's assume that the rabbits don't die. On month 0, we start off with our pair of baby rabbits, 1 pair in total. On month 1, the pair is matured, but we still only have 1 pair. On month 2, they produce their first pair, so we have 2 pairs in total. And on month 3, the new pair has matured while the first pair produces another pair, bringing us to a total of 3 pairs. And the goal here is to calculate how many pairs of rabbits we'll have by the nth month. Notice, the total number of rabbit pairs will be the sum of the pairs from the previous month and the newborn pairs. Since newborn pairs are produced by pairs that are at least 2 months old, the newborn pairs are just the number of pairs there were 2 months ago. This means the number of pairs in month n will be the sum of the number of pairs in month n-1 and the number of pairs in month n-2. Of course, n has to be bigger than 1 for this to work, since there aren't any negative months. But we already know that at month 0 and month 1 we only have 1 pair, so we could define those spots to be 1. With that, the sequence of pairs on each month goes like this, each term being the sum of the previous 2. The sequence is famously known as the Fibonacci sequence, named after its discoverer, Leonardo Fibonacci, who posed this problem in the 13th century. But some of you might already see the flaw in this approach. Suppose you want to predict the number of pairs after 1000 months. The 1000th Fibonacci number is the sum of the 999th Fibonacci number and the 998th Fibonacci number, which leaves us stuck with the exact same problem. How do we find those numbers? Ultimately, to calculate the 1000th Fibonacci number, you'd have to calculate the entire sequence leading up to it, which is a pretty daunting and tedious task. What we want is a closed form expression, meaning a formula which we can type into a calculator and get any Fibonacci number we want directly, without having to calculate the ones that come before it. Okay, this is where the math starts to kick in, so it's best if we take a minute so we can all get on the same page. In this video, we're going to be using matrices and vectors a lot. If you already know about vectors, matrices, and how to multiply them by one another, then you can skip to this timestamp. For anyone who doesn't, stick with me here, I'll explain everything. First, let's start with vectors, specifically 2-dimensional vectors, which is what we will be dealing with in this video. We have 2 ways of representing vectors, an algebraic way, where a vector is a pair of numbers, and the geometric way, where a vector is an arrow on the plane. Both representations are connected in the sense that the pair of numbers are the arrow's coordinates. One thing we can do is add 2 vectors together. In the algebraic representation, this means adding the corresponding terms, and in the geometric representation, this means connecting the arrows together tip to tail. And interestingly, both of these representations express the same thing. We can also multiply a vector by a number. In the algebraic representation, you multiply each term by the number, while in the geometric representation, you stretch the arrow by that number. Again, as you might have guessed, both of these representations express the same thing. Now, let's get on to matrices. A 2x2 matrix, which is the type of matrix we will be dealing with in this video, is a 2x2 grid of numbers. Adding 2 matrices together is done term by term, and the same goes for multiplying a matrix by a number. It's just multiplying each of the terms by that number. Now this is where things get interesting. We can multiply vectors by matrices. The idea is to split the matrix's columns into two vectors, multiply each column by its corresponding term in the vector, and add the two columns like vectors. We can also multiply two matrices together. The way we do it is by splitting the right matrix's columns into two vectors, and then you multiply each vector by the left matrix. Finally, you connect the two resulting vectors into the resulting matrix. I know that all of this is a lot and the formulas are really weird. No need to memorize any of these. The only thing that is important is the concept. If these concepts aren't sitting right with you, then it might be a good idea to check out 3 Blue 1 Brown's series, Essence of Linear Algebra. Chapter 1 to 4 will do you good. But I recommend watching the entire series if you can. The series won't just put you in a better position to understand this video, but in a better position to understand math in general. One thing that will prove to be useful in this video is going the other way around. Just like how we can take out a common coefficient from an expression, we can take out a common coefficient from matrices and vectors. We can even take this a step further and take out a matrix. What I mean is if we have a vector, let's say x plus y, x, we can express the vector as the vector xy multiplied by some matrix. The way we find that matrix is just going through the matrix vector multiplication, but in reverse. X plus y x can be expressed as the sum of two vectors. One vector is multiplied by x and the other is multiplied by y. To find these vectors, just think how many times does each variable appear in the top and in the bottom. For example, x appears once on the top and once on the bottom, so the vector will be 1, 1. On the other hand, y appears once on the top, but it doesn't appear on the bottom at all, so the vector will be 1, 0. From there, arrange our two vectors to be the columns of a matrix, and there we go. We got the matrix 1, 1, 1, 0, and when we multiply the vector xy by that matrix, we get the vector x plus y, x, which is what we want. There are also some special matrices. One is called a diagonal matrix, where there are values on the diagonal and everywhere else is 0. What's special about it is that multiplying two diagonal matrices by one another is just multiplying the corresponding terms by one another. Another special matrix is the identity matrix. It's a specific diagonal matrix where all the values on the diagonal are 1. What's special about the identity matrix is that multiplying vectors or matrices by it does nothing. Some matrices also have something that is called an inverse matrix. Just like how in regular numbers we can multiply a number by its inverse to get 1, we can multiply matrices by their inverse to get the identity matrix. Okay, this is all we need for this video, so with this, let's get back to our rabbits. To start off, we already established that the number of rabbit pairs in a certain month will be produced by the number of pairs in the previous 2 months. So it might be a better idea to look at pairs of months instead of looking at each month individually. We can use a vector to represent the number of rabbit pairs in a certain month and the number of rabbit pairs in the previous month. So for month 1 and 0, we'll have the vector 1, 1. For month 2 and 1, we'll have the vector 2, 1. For month 3 and 2, we'll have 3, 2. And for month 4 and 3, we'll have 5, 3. Notice that in this way of grouping months into vectors, each vector produces the next one. In general, the vector xy will produce the vector x plus y, x. This operation can be represented by multiplying the vector xy by the matrix 1, 1, 1, 0, which I will call A for the rest of the video. We can start off with the first vector, 1, 1. Multiply it by A and we get the second vector, 2, 1. Do that again and we get the third vector, 3, 2, and so on. So we can get the nth vector by multiplying the first vector by a to the n. And notice that the second number in the nth vector is the nth Fibonacci number. This means that by calculating a to the n, we can calculate the nth Fibonacci number directly. But the problem is calculating a to the n. It is just as hard as calculating the nth Fibonacci number, if not worse. This is because matrix multiplication is so wacky. While this is a clever approach, it seems that we have ended up taking one step forward and then 2 steps back. What we want is to find a clever way to think of our matrix A, in a way which will make it easier to calculate a to the n. One idea is multiplying a vector's coordinates by a and seeing where it takes the vector on the plane. Now what I want you to imagine is changing our coordinate system, scaling and rotating each axis while keeping our vector in the same place. Again, multiplying a vector's coordinates by a, we end up with a completely different vector than what we got before. Now, the question is, can we change a as well, to match the new coordinate system? Is there a different matrix, let's call it B, that describes the same operation as A, but from the perspective of a different coordinate system? In fancy math terms, we say A and B are similar, since they symbolize the same operation but from different perspectives. And notice that since A and B represent the same operation, doing each one of them n times is the same. So it follows that a to the n and b to the n are also similar. And this is great, because if b were a simpler matrix than a, one where calculating b to the n is straightforward, we could utilize this to find a to the n. For example, if b happened to be a diagonal matrix, then raising it to the n is as elementary as raising its individual components to the n. Now, in order to find b, we need to make this observation. The only difference between a and b is the coordinate system itself. So in order to find b, we need to be able to translate between these coordinate systems. We need to find a way to understand how a vector described in the language of one coordinate system translates into the language of another. When we represent a vector with coordinates like 3, 2, it means that to get to the vector's tip from its tail, we need to take 3 steps to the right and 2 steps up. Conversely, a vector with coordinates -5, -1 indicates a need for 5 steps to the left and 1 step down. But the question is, what exactly do we define as a step? For our purposes, let's define a step to the right as going along this vector, and the step up as this other vector. These vectors that define our steps, known as I hat and j hat, are what we call basis vectors, and together they form a basis. In this specific case, they form the standard basis, which creates the standard coordinate system we are familiar with. But the beauty of bases is in their flexibility. We can redefine our steps, or more formally, we can redefine our basis vectors. And this is what we mean by changing the coordinate system. It's just changing what we define as a step. So now, the vector which previously had the coordinates 3, 2, now has the coordinates -1, 1. A quick note is that these basis vectors can't be on the same line, since you need 2 step vectors that point in different directions to traverse the plane freely. Now we want to be able to convert between coordinate systems. Let's say we have some basis u that we're interested in, and we have a vector whose coordinates are given to us in u's system. What we want is to find the standard coordinates of the vector. Let's call u's basis vectors u1 and u2, and let's suppose we have their standard coordinates. By the coordinates of our given vector, we can tell how many steps along u1 and u2 we need to take to get to the vector's tip. But since we have the standard coordinates for u1 and u2, then we could represent these steps as standard steps, as in going along I hat and j hat. This gives us a way to represent our vector with I hat and j hat steps, which gives us the vector's standard coordinates. But the beauty of all of this is that we can do this entire operation by multiplying the vector's coordinates x, y by a matrix whose columns are the standard coordinates of the basis vectors u1 and u2, which we call a transition matrix. And going the other way around, getting from the standard coordinates to u's coordinates, is even more beautiful because it's just multiplying by the inverse of the transition matrix. In essence, while the transition matrix takes us from u's coordinate system to the standard coordinate system, its inverse brings us back from the standard coordinates to u's coordinates. And to recap why we're doing all of this, remember, we're trying to find a matrix that represents the same thing as multiplying by A, but from the perspective of a different coordinate system. To do this, let's use a transition matrix to convert from the different coordinate system to the standard coordinate system. And now that we're in a familiar environment, we can multiply by A with no problem. After that, we convert back to the original coordinate system using the inverse of the transition matrix. Expressed as one matrix, B is the product inverse M times A times M. So now, the only mystery that is left to solve is which basis will make B a diagonal matrix. Okay, so we want to find a basis that will cause our similar matrix to be diagonal. Now, to find this basis, we need to consider what properties this basis will have. It never hurts to name things, so let's call the basis U and the matrix similar to A with respect to U as B. One thing that is true for any basis is if we look at the basis vectors, let's call them U1 and U2, their coordinates in U's system will be 1, 0 and 0, 1 respectively. This is because they are the definition of a step, so it follows that each one of them will be exactly one step. When we multiply U1's coordinates by B, we find something interesting. We get lambda 1, 0, which is a scaled version of U1 that is scaled by lambda 1. And when we multiply U2's coordinates by B, we get a scaled version of U2, scaled by lambda 2. One helpful way to look at these vectors is that their slope doesn't change after multiplying them by B. Since A and B are similar matrices, the same property should hold when we multiply U1 and U2's standard coordinates by A. We call vectors that are scaled when multiplied by some matrix eigenvectors of that matrix, and the factor in which the vector is scaled is called an eigenvalue of that matrix. So U1 and U2 are eigenvectors of A, and lambda 1 and lambda 2 are eigenvalues of A. This means that the basis we're looking for will be constructed from eigenvectors of A, and the values on the diagonal of the similar matrix will be the eigenvalues of A. Some of you might point out that any number is an eigenvalue by looking at the 0 vector as an eigenvector, and because of that, we don't count the 0 vector as an eigenvector. Now, let's find these eigenvalues and eigenvectors. We're trying to find vectors that are scaled when multiplied by A, so we can create a system of equations like so. First, let's solve for the eigenvalues. We can plug lambda y into x to create this, and we can deduce that y can't be 0, else x will also be 0, and then we have the 0 vector, which as we said, does not count. Because of that, we can divide both sides by y and get this equation. And solving for lambda, we get two eigenvalues. First one is 1 plus square root of 5 all divided by 2, which is famously known as the golden ratio, denoted by phi. The second eigenvalue is 1 minus square root of 5 all divided by 2, which can be simplified to 1 minus phi, which we denote as psi. Using these two eigenvalues, we can easily find an eigenvector for each eigenvalue. Now, the golden ratio is defined as the only positive number that is one more than its inverse. But this leaves us with an interesting question. What does the golden ratio have to do with counting rabbits? And why does it appear as an eigenvalue of A? To answer this, let's look at a different question we could ask about the rabbit problem. What is the ratio between the mature rabbit pairs and the baby rabbit pairs at a certain month? As we already discussed, the number of mature pairs will be the number of pairs there were the previous month, since the number of pairs there were the previous month are now all mature. And the number of baby pairs will be the number of pairs there were 2 months ago. So the ratio between the mature pairs and the baby pairs at month n will be fn-1 divided by fn-2. If we look at this ratio for a certain month, it doesn't look really interesting. But if we go through the months, each time measuring this ratio, notice that it seems to hover around the golden ratio. And the more the months pass by, it approximates the golden ratio better and better. This leads us to a new topic called convergence. If you are already comfortable with the concept of convergence, feel free to skip ahead to this timestamp. But if you don't know what it is or need a refresher, then stick with me here. Let's look at this sequence which goes 1/2, 1/4, 1/8, 1/16, and so on. If we were to plot the terms of the sequence on the number line, as we plot more and more terms, the sequence sort of locks in on 0, getting arbitrarily closer to it. We say that the sequence converges to 0, and this is the notation where lim stands for limit. Another example is the sequence which goes 1/2, 3/4, 7/8, 15th, 16th, and so on. If we plot the sequence, we see that it converges to 1. For our specific problem though, just looking at the terms on the number line isn't enough. We want concrete proof that the sequence actually converges to the golden ratio. Maybe the sequence converges to a different value, close to the golden ratio, but not exactly it. What we want to show is that the sequence must converge to the golden ratio, no ifs and no buts. Let's see how we can do this. Let's call the sequence of ratios between the mature rabbit pairs and the baby rabbit pairs at month n, Rn, and the number it converges to, x. Now, Rn plus 1, which is like shifting the sequence to the left, also converges to x. Now, we know that Rn plus 1 equals Fn divided by Fn minus 1. And we know that Fn equals Fn minus 1 plus Fn minus 2. Plugging that in and doing some cancellation, we get 1 plus Fn minus 2 divided by Fn minus 1, which is 1 plus the inverse of Rn. And we know that Rn plus 1 and Rn converge to x. So by looking at the convergence, we have x equals 1 plus 1 divided by x. This means that x is 1 more than its inverse, and as we said, the only positive number that satisfies this is the golden ratio. As for why the golden ratio appears as an eigenvalue of A, we can rearrange the definition of Rn to get that Fn minus 1 equals Rn times Fn minus 2, and that Fn equals Rn plus 1 times Fn minus 1. If we take the vector Fn minus 1, Fn minus 2, and multiply it by A, through the properties of A, we get Fn, Fn minus 1. And plugging things in, we get Rn plus 1 times Fn minus 1, Rn times Fn minus 2. Dividing both sides by Fn minus 2 and doing some cancellation, we get A times Rn, 1, equals Rn plus 1 times Rn, Rn. And we can take an Rn out of there to get A times Rn, 1, equals Rn times Rn plus 1, 1. Finally, since Rn and Rn plus 1 converge to the golden ratio, when we look at the convergence, we get A times phi1 equals phi times phi1. Meaning the golden ratio is an eigenvalue with the vector phi1 being an eigenvector. Okay, we're almost done. Let's just recap for a second what we have done so far. we have transformed our rabbit problem into a different problem, calculating a to the n. We talked about matrices that are similar to A in the sense that they transform vectors in the same way, just from the perspective of a different basis. We then found a way to actually calculate these similar matrices given the basis they're in. We then found that if we construct a basis out of eigenvectors of A, the similar matrix will be diagonal, with the values on the diagonal being the eigenvalues. Finally, we found those eigenvectors and eigenvalues. We have found two eigenvectors, which will be our basis vectors, which we can use to create a transition matrix, let's call it M. We already know that the similar matrix, let's call it B, is guaranteed to be diagonal, with the corresponding eigenvalues on its diagonal. Using our formula for similar matrices, B equals inverse M times A times M. But remember, since A and B represent the same operation, doing each one of them n times is the same. So A to the n and B to the n are also similar, which means that B to the n equals inverse M times A to the n times M using the same formula. Rearranging, we get that A to the n equals M times B to the n times inverse M. And since B is a diagonal matrix, calculating B to the n is straightforward. This means that we now have a direct way to calculate A to the n, which gives us a closed form expression for the nth Fibonacci number. Okay, we're basically done. I just want to point out that there are other forms of the Fibonacci sequence. In the rabbit problem, we start the sequence with 1, 1, and then the rest of the sequence is determined by the relation. We call those two elements in the start the starting conditions. By changing these starting conditions, we change the entire sequence. For example, we can start with 0, 1, or maybe -1, 4, or wherever you want. For our problem, we used the vector 1, 1, since the starting conditions were 1, 1. But if the starting conditions were -1, 4, all we have to do is change the vector to 4, -1, with f1 being at the top and f0 being at the bottom. This way, we get a closed form expression for any form of the Fibonacci sequence. I also want to finish this video off with a challenge for the computer scientists out there. As a matter of fact, the closed form expression for the Fibonacci sequence isn't the best when it comes to applying it in the real world. What I mean is, if you were to make a program which calculates the number of rabbits at month n, the closed form expression isn't the optimal approach. Here's the challenge. First, point out the problem with the closed form expression. And secondly, how would you go about calculating the nth Fibonacci number optimally? I would like to see your approaches in the comments. This video is my entry for the third Summer of Math Expedition by 3Blue1Brown and James Schloss. If you made it until here, you are probably interested in stuff like this. In that case, you should check out the other submissions as well. If you have any questions about this video, feel free to leave a comment or contact me through these platforms. This video was really fun to make, and I'm probably going to make a part 2 for this video, where we generalize. What we did here in this video, finding a similar matrix to A, which is also diagonal, is called diagonalization, and it is a super useful tool in mathematics. And it can be used to find a closed form expression for an entire family of sequences. So, I might make a video about that. Anyhow, be cool, stay in school, and do math.